Hello, my name is Nicholas Kasanovic, and this is the supplementary video presentation for our research entitled Biomimetic Real-Time Multimodal Tactile Perception and Haptics for Telepresence Humanoids. A complete video presentation will be available upon publication. Robotic telepresence enables people to remotely conduct crucial work or connect with others through the body of a physical robot avatar. We aim to improve avatar systems by enhancing the architecture and methodology used to provide both agents and operators with a sense of touch. In this research, we address three critical gaps found in other telepresence systems, being 1. Deterministic tactile sensing. Typically, robot agents cannot classify the textures of objects. Instead, they relay high-frequency data streams to haptic gloves, forcing operators to classify sensations. Our proposed methodology uses vibration analysis to quantify object roughness. 2. Network efficiency. High-frequency haptic data streams take indispensable network bandwidth from critical subsystems. In contrast, our approach determines texture, so low-frequency streams can be used, relaxing network usage. 3. Intuitive multimodal haptics. Using unnatural sensing strategies and vibrational feedback to feel both forces and textures can be confusing for the inexperienced. Contrarily, our system exploits psychological behavior and multimodal haptics to mimic natural human touch. The proposed system was curated for human intuition. Thus, the exploratory procedure of lateral fingertip motion is used for tactile sensation. This is seen on the left, where an operator rubs the agent's anthropomorphic fingertip against a smooth rock to feel its texture. Generally speaking, Avatar-Hubo's system uses VR and motion capture equipment to immerse its operator in a virtual environment. Its haptics system is no exception, introducing wearables like the Manus Quantum Meta Gloves and WeArt Touch Diver to the operator. Additionally, a modified, highly dexterous humanoid manipulator is fitted with a SynTouch Pneumatac sensor on its fingertip and is used to gauge tactile properties. Here is a graphical representation of Avatar-Hubo's end-to-end haptics system architecture. The color code is as follows. Green blocks represent sensors, blue blocks represent actuators, light gray blocks represent computers and peripherals, dark gray blocks represent software, and gold blocks represent network infrastructure. Starting from the top left, Manus Core samples the quantum metagloves to recreate the operator's hand in Unity. Then, Biomimetic, an IK solver based on genetic algorithms, maps the operator's hand pose to a virtual robot hand. Corresponding joint angles are then sent through Rossbridge to Avatar-Hubo's Extra PC, which commands the physical robot's hand to move. The hand responds by feeding measured joint positions to the force calculator. Additionally, the texture calculator samples and processes high-frequency dynamic measurements from the Pneumatac. Next, the texture and force calculators independently send data to Unity, which prompts the WeArt middleware to command the Touch Diver's actuators, creating sensations of force and texture. Rapidly converting measurements to tactile feedback is a challenge in Avatar robotics. We propose a real-time haptics method that exploits lumped calculations and integrated delays to synchronize visual and haptic feedback. The real-time haptics method is composed of two parts: the lumped model texture detector and the delayed encoder force array. The former uses our lumped roughness metric to lump vibrational mechanics into a single roughness value R, where higher values indicate rougher textures. This equation uses discrete Fourier transforms of live data, which have an associated time delay. By varying sampling parameters, one can adjust the haptic time delay. For example, previous research found that Avatar-Hubo's average visual latency was approximately 0.5 seconds. Thus, visual texture synchronization is achieved by equating the haptic time delay to the visual latency. The real-time haptics method also contains a delayed encoder force array, which stores forces derived from a virtual variant of Hooke's law in real time. The array is of prescribed size, only containing the m+1 most recent forces. After calculating the array, if each of its element values are above a set low force threshold, the most recent force is transferred to the Dutch diver. Because the array's elements change dynamically, its size is directly proportional to a time delay. Furthermore, larger arrays are more robust against noise and short spikes in force data. Thus, with tuning, the delayed encoder force array delivers force feedback with visual force synchronization. A major benefit of this proposed methodology is also its bandwidth efficiency. Force feedback updates at a modest 20 Hz, while texture updates at 2 Hz. These low frequencies constitute insignificant network consumption, freeing up valuable bandwidth for vision or motion systems. Now, on to our trials. In our first experiment, the static test, the lumped model texture detector's accuracy is verified by rubbing 2 distinctly textured rocks on the pneumatic by hand while the HDHM is fixed to the table. 3 plots are visible in the background. The plot on the left displays 1,024 pressure samples captured in the last half second from the pneumatic. The middle plot shows the associated amplitude spectrum. Finally, the plot on the right depicts the calculated lumped roughness values over time. By setting thresholds, we can associate lumped roughness values with textures. Furthermore, the plot's title displays the current texture determined by the thresholds. So if I was to take something like a smooth rock, for example, and rub it against the sensor, you can see it says smooth, and the faster I go, typically the more accurate readings I get. Just taking it away, it goes away. If I was to go strike it like so, smooth, and then back to nothing. If I was to take something textured like this rough rock instead and then rub it against the sensor, you can see much higher numbers come up. And the faster I go, the more accurate my readings are. As seen in this plot, the lumped model texture detector can correctly identify textures over 80% of the time the sensor is in contact with material. In our second experiment, the dynamic test, the lumped model texture detector identifies the textures of rocks fixed to the table while being moved by a human. The sample 3 plots are visible in the background, with the same sampling rate, number of samples, and thresholds. Okay, so that was the first one. Now if we go to the smooth rock instead, you can see it very simply says smooth. As shown by the title of the plot, the lumped model texture detector could identify texture in both the static and dynamic tests. Additional results from the static test are displayed here. AC pressure, amplitude spectra, and transient lumped roughness value plots are displayed from left to right. From top to bottom, one can see the associated plots for contact with each object, including no object contact, smooth rock contact, and rough rock contact. Note the difference in AC pressure and amplitude spectra between the rough and smooth rocks. The rough rock contained more high-frequency data, supporting the assumptions made when developing the lumped model texture detector. Additionally, the plots on the right show that the proposed methodology clearly produces different signals for contact with each object based on their texture. For our third and final experiment, the telepresence test, both the lumped model texture detector and encoder-based force arrays are verified by having a human operate Avatar-Hubo with its proposed haptic system. The human operator is tasked with feeling 4 different objects fixed to a table: a smooth rock, a very rough rock, a very smooth pipe, and an intermediately rough artificial plant. After feeling an object, the operator had to verbally announce what texture they felt.
Yeah, we're gonna do that.
Okay, you ready, Nate?
Okay, you ready, Nate?
You're good.
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 Smooth,
Smooth,
rough,
rough, Smooth. Smooth. Smooth roughish. Smooth roughish.
Okay.
Here are the results of the telepresence test. On the left, we have a plot of perceived roughness over time. The blue shaded region represents smooth textures, and the red shaded region represents rough textures. For the most part, the smooth rock and the smooth pipe were considered smooth. The rough rock was considered rough, and the artificial plant was considered an intermediate roughness. Note the large spike in the plant's data labeled impact noise. This noise resulted from the pneumatic rapidly colliding with the solid trunk of the plant, causing high-frequency skin vibrations. Nonetheless, the short bursts in lumped roughness value stabilized before the next measurement, letting the system function normally. Furthermore, the impact noise's brief nature prevents it from adversely affecting the operator's macroscopic experience. On the right, we have a transient plot of average forces from the delayed encoder force array. The blue region represents forces that saturate the touch diver's force actuator, and the gray region represents minuscule forces not transferred to the touch diver. Also, the plot has annotations showing the response of the method when the robot's hand touched each object. Moreover, force values spike when object contact occurs, actuating the touch diver and creating a sense of force feedback. Because the real-time haptics method uses two independent processes, the operator is able to feel forces and textures simultaneously. Furthermore, the operator was able to correctly recite object textures 95% of the time, supporting the proposed method's efficacy. Overall, our proposed end-to-end haptics system allows human operators to feel forces and textures through a physical robot agent in real time with visual synchronization and bandwidth efficiency. Despite our real-time haptics method's capabilities, improvements can be made to increase multimodality and stability. For instance, by adding temperature sensors to the HDHM, one can use the touch diver's Peltier module to enable temperature feedback, another tactile mode. Additional filtering can be added to the lumped model texture detector to mitigate impact noise effects, improving robustness. Also, mapping arm joint currents to a haptic suit could enable the sensation of weight during object manipulation. Thank you very much for watching.